So when you treat objects as point particles, there's really only one way to frame Newton's second law. It simply says that the net force acting on an object is going to be equal to the object's mass times the object's acceleration. But now that we've changed how we're modeling particles, and so we have extended objects that have a center of mass but then extend out around that center of mass, we actually need to change the way we frame Newton's second law. Or the equation that we've dealt with up until now, we're going to reframe as the translational version of Newton's second law. So we're still going to have F net equals ma. It's just we want to be clear about what this translational version of Newton's second law is telling us when we have extended objects. So the first thing is it describes the center of mass motion of a rigid object. Second is it tells us how the vector sum of the forces acting on the object change how the center of mass of an object moves by causing the center of mass to accelerate. 3. The equation tells us that the net force acting on the object and the acceleration of the object always point in the same direction because mass is always a positive scalar. 4. That positive scalar mass is a measure of an object's resistance to being accelerated. So the larger you make the mass, the harder it is to change an object's center of mass motion. But what we've seen in going from point masses to extended objects is that, of course, we now have more than just translational motion. We also have rotational motion, and that gives us a rotational version of Newton's second law. So explicitly what this equation is it's taken all of our translational quantities and swapped them out for our rotational quantities. So again, notice that instead of the net force on the left-hand side of the equation, we have the net torque. Instead of mass, we have the moment of inertia, rotational inertia, whichever way you want to label it. And then again, instead of the acceleration, we have the angular acceleration. So the rotational version of Newton's second law tells us that the net torque acting on our object about some pivot is equal to the moment of inertia of that object about some pivot point times the object's angular acceleration. So what does this rotational version of Newton's second law tell us? Well, it describes how a rigid object rotates about its center of mass. So if our F net equals ma described the center of mass motion, the net torque equals I alpha describes the rotational motion of the object. 2. It says that the vector sum of the torques acting on the object change how the object rotates about its center of mass by causing an angular acceleration. 3. The net torque and the angular acceleration always point in the same direction. And again, for us, always pointing in the same direction means they're going to point in the same direction along the axis of rotation. The reason the net torque and the angular acceleration always point in the same direction is again because the rotational inertia is always a positive scalar. Well, that positive scalar is a measure of an object's resistance to having its rotational motion changed. So mass is a measure of how an object resists having its translational motion changed. The moment of inertia is a measure of an object's resistance to having its rotational motion changed. So when we're working with our translational equation, again, fundamentally, it's a vector addition problem. We're going to draw a free body diagram that shows all the forces acting on our object, and then we're going to break those forces up into x and y components. We're going to break the acceleration up into x and y components, and so we can set up one equation per coordinate axis that we need. Or if we only have forces acting in a single dimension, then we only need one equation. If we've got forces acting in x and y, then we're going to need two equations. With those two equations, we need to break the force and acceleration vectors up into their components. And so it's just worth highlighting again that both the forces and the acceleration are vectors. Right? It's often easy to forget that the acceleration in this equation is also vectors that we also need to break up into its components correctly. So for the rotational version of Newton's second law, again, fundamentally, it's a vector addition problem. The nice thing about problems we're going to work in this class is that, of course, it ends up being a one-dimensional problem. We'll be able to draw forces that act in the x and y directions, but they'll rotate, or they will cause torques about the z-axis. So we'll set up some of the forces in x, some of the forces in y in terms of our translational equations, but we'll have a single equation for the sum of the torques in z. Again, we need to break torque and angular acceleration vectors up into components, and both the net torque and the angular acceleration, they're vectors. The nice thing again here is, because this is really a one-dimensional vector problem, breaking vectors up into components in a one-dimensional problem is really all about paying attention to the signs. And so here's a situation where if we pay attention to our signs correctly, so that we get all the signs right for our individual torques, we pay attention to what the sign is for the angular acceleration, then we're going to come out with the right answer in our rotational Newton's second law problem.